We are on page 52. Applications to speed, time, and velocity. So now we take our vector equation of the line, where you have the position vector of any point, some particular point, and our direction vector, and we apply this equation to speed, time, and velocity. So what does that mean? Instead of r being the position vector of any point on a line, we say it's position vector of any point of the path of a moving object. And we have a starting point, A, not just any point on the line, because that starting point is when t is 0. And t will stand for time. Our direction vector is now our velocity vector, because our velocity vector will tell us how far we're going in 1 unit of time. And the length, or the magnitude of our velocity vector, is the speed of the moving object. So here we have two-dimensional vector. We've got a starting point at 1, -1, a velocity vector at 3, 4. And these vectors represent going east and north. So if you would go 1 in the positive x direction, as this first vector shows, that would make sense of going 1 unit to the east. And if you would have a 1 there, that would be a positive 1 y value, which would be 1 to the north. If you wanted to go to the south or to the west, you'd have negative values. Time is an hour. So write down the velocity vector. Our velocity vector is the 3, 4, and the speed, if we find the length of that vector, we get the square root of 3 squared plus 4 squared, which would be 5. But now we need to put units in here, since we were dealing with kilometers and hours. Our speed is 5 kilometers per hour. If we wanted to describe the motion of this object, the object is moving at now, how would we describe this direction? What's the best way of describing a direction that you're going like 3 east and 4 north? Or, you know, you could put the direction vector so the direction that 3 east and 4 north, you could figure out an angle for that, but that describes the motion of this vector at that point. Part C here, give the equation of the path in ax plus by equals c form. Well, how have we done this in the past? We've started with our vector equation, which we have. You could take your vector equation and create your parametric equation. So from r's it'll be 1 plus 3t, and our y would equal -1 plus 4t. From our parametric equations, you could solve for t, and solving for t will give us our Cartesian form. And in the first equation, solving for t, I'd get x minus 1 divided by 3. The second equation, solving for t, I get y plus 1 divided by 4. And that's our Cartesian form. And the Cartesian form is the one that you can manipulate to get into y equals mx plus b, or any form of the line. In this case, we want ax plus by equals c. So I would multiply both sides by 4 and both sides by 3. Get 4x minus 4 equals 3y plus 3. And rearrange things, and we get 4x minus 3y equals 7. So our second example here, we've got the parametric equations given to us. Time is measured in seconds, distances in meters. Write down the vector equation. So from our parametric equations, we know that our starting point is 4, 5. And our direction vector or velocity vector is 5, -2. So write down our velocity vector. And from our velocity vector, if we find the length of it, we will get the speed of the object. And then we introduce the underlying theme of today's lesson. A pole is located at 39, -9. Will the object collide with the pole?
Depends on how wide the object is.
Okay? And so what this question is asking in its real-life application is whether or not this coordinate or this point, is it on the equation of the line or not? We already had our parametric equations. We knew that, and I don't know if you've noticed in today's lesson, well, probably more in yesterday's lesson, that we tend to use the parametric equations a lot when solving for things. So we've got our two parametric equations here, and you're wondering if the point 39 and -9 are on this line. So if I look at this situation and solve for t, I get t equals 7. If I check the y coordinate, I get t equals 7 again. And since they're both at the same time, yes, unfortunately, this moving object will hit the pole.
Maybe that's a good thing. Maybe that's a good thing.
Maybe it is a good thing. Maybe this is a mosquito that you have been pursuing for a little more than 30 minutes, and finally it runs into the pole. Well, and it's also interesting that the mosquito has decided to travel on a straight line, which is probably quite rare.
Well, it's because the mosquito lost a few brain cells. It's meters per second.
Yeah. It is meters per second, huh? 5 meters per second, that's pretty good.
Maybe he's got the baby behind him. Maybe he's not even making a choice.
Maybe blown along and hits the...
He's trying to fight
Yeah.
back.
There you go.
A normal Canadian wind.
A jet is flying at 700 kilometers per hour in the direction of 263. Find the velocity vector. So what we need is we need a vector that is parallel to this one, and its length needs to be 700. Because remember that the length of your velocity vector is your speed. So the best idea, exactly, if we find a unit vector, so I'll just label that with u even though we don't have any labels here. If we find the unit vector for this one, that's going to be 1 over the length of this vector. And if I find the length of this vector, it is 2 squared plus 6 squared plus 3 squared, which is a very nice number, adds up to 49. So we get 1/7. Okay? And now we can multiply it by 700. Another way you could do this one is you might have figured out, oh, this vector has a length of 7. If I would want a length of 700, I would just have to multiply by 100. But usually you're going to find the unit vector first because it's not often that the numbers work out that nicely. So we get our unit vector first, we multiply that by 700, and I'll show all the work, even though 200, 600, negative 300. A yacht leaves a harbor and its position vector is given by the following equation. So the harbor is located at 0, 0 in this equation because that's its starting point. Cargo ship is not at the harbor, and at that same time its vector equation is as follows. So its position relative to the yacht at the beginning, it's at 6,3 at the same time the yacht is at the harbor. Find the speed of the yacht. So we need to figure out which is our velocity vector from which equation. So we go to our equation with the yacht. 25 plus 64, square root of 89, and everything is given in kilometers per hour. So, pleasure boat, nice. Yes, so we are now calling our yacht a pleasure boat. Very nice.
Actually, something on the IB exam. No, that's within our notes.
This is-
No, but I'm pretty sure this is from an old IB exam. Oh yeah, but they actually switched the words up during the exam.
And we've used this example ever since. Okay, so at t equals 0, because that's when the pleasure boat starts its journey, okay? At t equals 0, we know that the cargo ship is at, and if we use the equation all the way through, I can write it as like really fancy, but you can see that it's going to be 6,3 because t is 0. What is our 3,7? So at t equals 0, the cargo ship is at is at 6,3. The harbor is at 0, 0. How would you figure that out? Here's a picture. Here's 0, 0. Here's 6,3. You just need to find how far it is. You could just do a squared plus b squared equals c squared. So square root of 45, it is 3√5 kilometers away. So I just simplified the square to 45 there. Bum, 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 bum. If both the yacht and, yeah, because it's not going to stay a pleasure boat much longer. If both the yacht and the cargo ship continued on the same course, would they collide? So again, we're going to look at our parametric equations to see if they have a point in common. And you'll notice that in this equation, as opposed to some of our other equations that we've had so far, so here is, here is our one equation in blue, here is our other equation in green. And what's different from some of the equations that we've had so far, do you remember that we had t's and s's as parameters? But now, in this real-life example, time is not different for the two of them, right? And you can have two lines that cross that aren't catastrophic, right? There's probably lots of times that I've been on a boat on a lake and my boat has traveled across the path of where another boat once traveled across. And we're okay because it's not the same time.
Oh. I like in our
Right?
example, he used a different time frame for one. Like one was S and one was T. And I took a problem with that. And tried this. Maybe remember that.
So here, what we're going to do, yeah, same thing.
In R that they use like S and T.
Okay.
Like these different time frames. So you're just saying that they crossed at some point. Yeah, so my like they didn't actually collide.
So from our first equation, this solves that if they were to cross, it would be at t equals 2. And at our second equation, oh, sorry, t equals 3. Woo, perfect. Nice recovery. And our second equation also happens when t equals 3. So yes, the pleasure boat will no longer be a pleasure boat, because I would much rather be in the cargo ship when this happens.
Depends on how big the cargo ship. Maybe it's one of those drone cargo ships.
And our last example of our vectors notes.
Actually, that's a pretty long one.
There's a lot of writing here. So we've got our vectors representing north and east like normal. The diagram shows a radius of 25 kilometers with a center O being at 0, 0. And that's where a lighthouse is situated, on some sort of rock surrounded all the way by the sea. Now, if you're far enough away, you don't see the lighthouse. Perhaps it's foggy. Okay? And a ship at P, which is not where it is actually 31 kilometers west and 32 kilometers south. So that would be, yeah, well, that's close enough for labeling. There's point P. And the ship is moving parallel to the vector 4, 3 with a speed of 20 kilometers per hour.
What's that H negative 1?
It's just the H is divided by like kilometers per hour. Sometimes in physics they'll write H to the minus 1 instead of writing divided by H. An hour after leaving P, the ship is at point R. So write down the vector O to P. Well, O to P, we are going 31 kilometers to the west, so that would show up as a minus 31. And 32 kilometers to the south, that would show up as a minus 32. And this next question is one that gets a little bit tricky because there are a number of ways you can go about finding this that are wrong. Okay? And you'd feel like you've done it right. Okay? We want to show that the path of the ship can be represented by this equation. And the number one thing that students do wrong in a question like this is they use the equation and show it works. Okay? You're not allowed to use what you're supposed to show. You need to have your results and what you're given come up with that. So how do we do that? What do we know? we know that the starting point at time equals 0 is negative 31, negative 32. So that part of the equation, we know that that was given to us. What else do we know? We know the speed is 20 kilometers per hour. In the direction, was it 4-3? In the direction 4-3. What does that second statement allow us to find? We could find the velocity vector. To find the velocity vector, we would need to first find perhaps the unit vector in that same direction and multiply it by 20. So our unit vector in this same direction, well, if I do a squared plus b squared equals c squared, you can find that that length is 5. So we can use the unit vector, which would be 1/5 of 4-3. Multiply that by 20. To get 1612. The vector equation is therefore going to be negative 31, 32 plus t 16, 12. Okay? The tempting thing to do in this question is to take the 16, 12, find the length, and say the length is 20, show that it's parallel to 3, 4, and then say 16, 12 works. Okay? But you're not showing, you're showing that the 1612 works by starting with the answer. And that, as far as mathematical proof or mathematical logic goes, you want to instead take the information that you know and show it to be what you want it to show, rather than taking what you want to show and show that it works. Does that make sense?
Yeah.
Okay. Find the vectors OR and PR. Remember, OR is where you're going to be after traveling 1 hour. So we can take our equation, plug in 1 hour, and figure out that where are we going to be? We're going to be at negative 15, negative 20. I guess I can even write this as, in particular, this is OR. And now if we wanted to find PR, right? There's a couple of ways we could find P to R. So we know P is here. We're traveling in this direction. We got to R. And we know from our origin here, we now know both of these vectors. You know that this one's at negative 31, negative 32. And you know that this one is at negative 15, negative 20. So you could use your old adding and subtracting vectors here, right? You could say if I want to go from PR, I could go PR go from P to O plus O to R. And that will work, right? And P to O is just negative of that one. And if you do those, you're going to find out that you get 1612. But you can also see if you're traveling in 1 hour from P to R, the direction that you're going is 1612, and you could see that directly from there. Okay? In this case, you could just write it down because it is sort of obvious from the question. Okay? Ooh. It spells words. Poor, maybe that's a poor decision. Poor decision would be to stay at P. That would be even worse if you wrote it all out. Okay. Show that when the ship reaches R, the lighthouse will first become visible. We know that the radius of the lighthouse is 25. So if we can figure out the length of OR, and if it is first becoming visible means that it would have to be exactly 25 away. If we do 15 squared plus 20 squared, sure enough, square root of 625, which is equal to 25. And maybe you recognize the 1520 is just a multiple of the 3, 4, 5 triangle. No. Right? It's 15, 20, 25 is just multiplying your 3, 4, 5 triangle by 5. Yeah, it's kind of, when you see it, it's sort of like, oh, I could have done this quicker.
We're just having Mr. Roth help us.
Yeah, I totally feel like I'd never get, like, if I saw, like, I was going to say a 10, 24, and, like, and 26, like, and then getting 26, because it would just be like a double of
5, 12, 13.
Like, I'd never look at them. So I'm like, you would just never.
And of course, to keep with the theme, a second ship path.
Is this pleasurable or
Well, no, it will also probably not end pleasurably.
that's good. I don't want to
Will be, so here is the vector equation. Figure out if those two boats will collide. Again, we go to our parametric equations. This one has parametric equations -7 plus 10t and y equals 4 plus 3t. Again, the same variable of t is used because we're talking about time, and it doesn't matter if the paths cross at a different time. It does matter if they cross at the same time. And our original boat's parametric equation, -31 plus 16t, and -32 plus 12t. Equating these two equations, -7 plus 10t equal to -31 plus 16t would give you 6t equal to 24, and 4 equals t. And in the second equation, if you equate them, 4 plus 3t equals -32 plus 12t. 9t is equal to 36, so t is equal to 4.
Are there any where they didn't collide?
No, I said there was a theme.
No, I have
It's-
the risk of them colliding.
I should have made one 3.9, so it's like they like just about narrowly missed.
0.999.
Really close.
They're real objects, not just lines.
Yeah,
There aren't point masses.
I guess you could have two lines as the outer and inner parameters of the.
But let's not.
What would happen if you found out t was the same in both, but they were both negative? Would they still collide?
No, because that's not possible.
What would that mean?
Means the
I
time-
mean, like 2 hours ago they crashed into each other, and now they decided just to keep on going?
It depends how the question is raised, I guess.
Maybe.
It's just 2 hours ago they